What's he doing?
He's making the wrong face!
Hey, Vsause, Michael here, and what do you say we get out of here to space and into an orbit? That way we could just float around and be free from the influence of gravity. Except not really. Astronauts orbiting around the Earth experience pretty much the same gravitational pull that you and I are feeling right now. The major difference is that those astronauts are falling constantly towards Earth, but their angular velocity is so large that they're falling just as fast as Earth curves away from them. Now, of course, this is nothing new. Tun's canon hasn't already taught us.
Gravity makes stuff fall, and in particular, Newton realized that it makes objects accelerate towards the Earth the same amount independently of how fast they're moving horizontally. That's called relativity. And of course, orbiting is just falling, but falling where you move horizontally fast enough that the Earth falls away faster. In order to successfully fall and miss the Earth, unless you dug a tunnel, you'd need to be traveling at almost 17,000 miles per hour, or 8 kilometers every second. So you'd probably incinerate from friction with the air well before you had a chance to enjoy the trip. Of course,
Newton's thought experiment involved the Earth, but on something smaller like the Moon, the cannon wouldn't have to throw its projectile nearly as fast for it to complete an orbit. In fact, if you had a powerful enough gun on the Moon, and you fired that gun at the horizon and then waited a little bit, you could get hit in the back of the head by the same bullet. Henry calculated that the bullet would have to travel about 1,600 meters per second, which is exactly how fast the Paris gun fires. Now that's a powerful gun, it's no squirt gun. But if you had a squirt gun out there in space and you fired a stream of water at the sun, how much water would it take to put out the sun? I mean, in general, putting water on something hot would cause that something hot to lose some heat, especially since the water will be frozen because it's out there in space. But here's the issue. The sun is not a big ball of hydrogen on fire. Instead, the sun is powered by fusion.
fusion of hydrogen nuclei, which is kind of like the chemical bonds between the hydrogen and oxygen that make up water, except on a much smaller and much more powerful scale. Now, before I get tackled by nuclear physicists from one side and chemists from the other, let me explain. A bond of any sort, whether between planets, molecules, atoms, nuclei, or quarks, is just a happenstance where two or more particles together have a lower total energy than when they were apart. Like if you get married and your taxes go down. So when you form a bond, that extra energy that the two solitary particles had is released. And because of a little relation we call E equals mc squared, this actually means that the mass of the pair goes down a little bit too. For example, every fusion reaction turns a little bit of hydrogenous mass into light. Sunlight, for example, amounts to a loss of 100 quadrillion kilograms each year. That's the equivalent of a medium-sized asteroid. But stars have a lot of mass.
And the more massive a star is, the hotter it burns.
And adding a bunch of water to the sun would only cause it to be more massive. So it would burn brighter, not go out. Of course, it would also burn faster, which means that its life would be shorter. For instance, if you were to add 20 solar masses of water to the sun, you would decrease its life expectancy from the current 5 billion years to only a few hundred million more years. But there's a faster way to put out the sun. Take that water or whatever material you want and shoot it into the sun in a way that causes everything to get spread out and scattered so that there's no longer the critical density needed for fusion to occur. Now, no matter which avenue of putting out the sun you pick, both would be a disaster. Literally. Disaster. From dis meaning against and aster meaning star. You would have literally turned our own star against us. If you were somehow able to avoid that disaster by magically appearing in intergalactic space, here's a fun experiment to try. Take out your gun and fire a bullet. That bullet will be forever alone.
That's because the universe is expanding, and if you were a few megaparsecs away from the nearest galactic cluster, on average those galaxies would be 200 kilometers farther away from you every passing second. In space terms, 200 kilometers a second is pretty slow. It's barely as fast as the solar system orbits the center of the Milky Way, and stars closer to the center of the galaxy can orbit 10 times faster. But a measly bullet travels only a few kilometers every second, and would have no chance of reaching the receding galaxies ever.
It makes you realize how tiny we are compared to the scale of the universe. But it also makes you realize how close together we all are here on Earth. Of course, to get from one side of the Earth to the other, you have to fly over half the sphere.
So what if instead there were a tunnel through the Earth? Let's jump over to my channel, Minute Physics, to see what happens. Click here, and I'll see you on the other side. Oh, and as always, thanks for watching.
Look who just sent me a text.
Addie McAllister?
What should I say?
Just play it cool.
Welcome to the world inside your phone, where everyone is expected to act one way their whole life.
Aw, snap! Ow.
Hey, Vsause Michael here, and when the pyramids of Giza were built, the tallest was 147 meters tall, making them the tallest things humans had ever built.
And they remained that way for nearly 4,000 years.
It wasn't even until the 1300s that we finally got around to making something taller, a cathedral in England. So, does that mean that the Great Pyramids of Giza are the best, tallest structures of all time? Well,
To find out more, all aboard the boat.
so what is a building? Well, technically, a building is a structure in which at least 50% of its height comes from floor plates where people can live, work, chill out. It has to be habitable. Any less than that, and it's not a building, it's a tower. After the Lincoln Cathedral finally surpassed the height of the pyramids, a number of churches continued to be built that kept breaking and setting new records. The next long-term record holder was the Eiffel Tower. It was the tallest thing ever in history that we had built for about 40 years in a row. It was finally surpassed by the Chrysler Building in New York, a personal favorite, which was then quickly bested by the Empire State Building. Now, the Empire State Building is interesting in that it was the first structure ever built by man that was so tall, were you to jump off the top of it, you would actually reach terminal velocity before you hit the bottom. It was the first structure we'd ever built that was so tall, rather than just continuing to accelerate as you fell, you would actually stop accelerating because you would reach the fastest possible speed your limp body can fall at. In the mid-1950s, something weird started to happen. Humans started to build radio and TV towers. These things could be way taller than the buildings that we'd made previously that had to be habitable. And so, ever since the Empire State Building had its record broken by a TV tower, all these other famously tall buildings, the Petronas Towers, Taipei 101, the World Trade Center, the Willis Tower, formerly Sears Tower, none of them have ever within their existence actually held the title for being the tallest thing we've ever built. There was always a radio or TV tower somewhere that was taller. Up until quite recently, and for quite a while, the record for the tallest thing ever built by humans went to the Warsaw radio mast in Poland. It's visually incredibly striking because there aren't any other skyscrapers around it. It's all alone, being very tall. Well, that was until 1991, where some workers exchanging guy wires made a mistake and the whole thing started to bend and then snapped in the middle. There's no video of the event happening, but it would have been similar to this collapse, though much, much taller. After the Warsaw radio mast collapsed, the KVLY TV mast in North Dakota became the tallest still standing structure built by man. But recently, buildings have made a comeback, and to check that out, we're going to have to travel to the Middle East.
This is the first time I've ever touched the Nile.
Ta-da!
Okay, so that was me dipping my waterproof camera into the Nile. If you were to take the entire length of the Nile River and stand it up on its edge, perpendicular to the Earth, it would reach into outer space about this far. It's pretty impressive. But where does the space shuttle orbit? And where does the International Space Station orbit? This far away? This far away? Maybe this far away. Actually, if this pink, inflatable, horrible boss's ball was the Earth, the space shuttle would orbit about right there. It's incredible, but it's possible because the shuttle and the International Space Station travel so quickly. They travel so quickly around the Earth that instead of seeing one sunrise and sunset every 24 hours, they see 16. But don't be jealous. You can easily see more than one sunrise and or sunset in a day by taking advantage of tall structures. So let's take a look at the tallest structure, the current record holder for the tallest thing humans have ever built, the Burj Khalifa in Dubai. The height of this building blows my mind. You can literally watch the sunset from the base of the building and then take a super fast elevator all the way up to the top and watch the same sun set again. In fact, the difference in timing between sunset at the base and the top is so significant, the Dubai Islamic Affairs Department actually had to make a ruling about when you can start and break your fast during Ramadan inside the building. People above floor 80 or higher have to actually wait to start eating 2 to 3 minutes after the people at the base because the sun hasn't yet set for those at the top. But before you head to Dubai to watch the sun rise or set twice in a day, keep in mind that the only height you actually need to see 2 sunrises or sunsets is the height of your own body. Try this the next time you're at a beach. Watch the sun rise or set over the water. Water is important because it won't have the terrain and hill issues that land does. Now let's say you're watching a sunset. Begin by laying on your stomach. Watch the sun set, and as soon as the very last little bit of the sun goes below the horizon, quickly pop up into a standing position, and voila, you'll see the sun's back, part of it's back, and it will set another time. If you take a stopwatch and record the time between the first setting and the second setting that you witness, and measure the height of your eyes when you're laying down and when you're standing, you can use those numbers to calculate the radius of the Earth. XKCD took this a little bit further by proposing the double sunset date. Take your date out to the beach in a cherry picker, and sure enough, it was calculated. Given the speed of a cherry picker, all you have to do is move about 6 feet up, and you can watch a beautiful sunset all over again. To put things in perspective, the Burj Khalifa is nowhere near as tall as Mount Everest, but the tallest structure that we could potentially build wouldn't be as tall as Mount Everest. It would be way, way taller, like into space taller. Of course, the problem with building things that are really tall is that they get heavier and heavier and have to support their own weight. But only up to a point. If a structure was so tall that it wound up at the altitude of a geostationary orbit, it would start to feel a new force, not just a gravitational force downward, but all of a sudden this new centrifugal force up and outward. And so a building that tall could be stable through tension and more than 35,000 kilometers high. This kind of structure is known as a space elevator. Unfortunately, there aren't any materials known to science today that are strong enough to make building something that large feasible, with the exception maybe of carbon nanotubes or boron nitride nanotubes. Of course, if we went to a smaller celestial body like the moon, we could build one today out of stuff like Kevlar. There are a lot of different things that we have to be wary of when we build a space elevator. For instance, how do we dodge space debris? One solution is to attach the Earth side of the cable to a boat in the ocean that can maneuver around and move the elevator away from dangerous obstacles. Another interesting point is that the taller the cable, the faster the far end of it will be traveling. In fact, if the cable is more than 50,000 kilometers long, its far end will be traveling near escape velocity, and simply walking outside could take you to the moon. But why build a space elevator? Well, because it would be awesome. but also for better reasons too. For instance, right now, in order to send a pound of material into orbit, it costs about $11,000. But with a space elevator, we could send the same amount of material into orbit for only about $100. That difference is so significant that Philip Reagan has said that the first country to deploy a space elevator will have a 95% cost advantage and will possibly be able to control all space-related activities.
Alright, so here you see in the mirror Alex playing guitar while she holds a camera in her mouth and records us. Impressive. I'm here with Kristen from Barely Political. She's visiting London. And if you enjoyed this episode of Boat, check out other episodes. I've got them all up there.
And as always, thanks for watching.
Oh, and check out Kristen's channel right there.
Bye.
Bye.
My name is Gene, and I'm supposed to be a meh. You know, like, meh, who cares?
Hey, Vsause, Michael here. In 2003, researchers did the measurements and found that Kansas is, in fact, literally flatter than a pancake. Of course, the Earth is not flat, the Earth is round. Otherwise, travelers would be falling off the edge all the time. Right? Wrong. If the Earth was not a ball shape, but was instead a flat disk, like this plate, well, with the right density and thickness, living in the middle could feel pretty normal. But as you moved toward the edge, gravity on a disk Earth would slightly skew, pushing at a greater and greater angle back toward the center. My friend Nick from Yeti Dynamics put together this great simulation. The person and buildings obviously aren't to scale, but check out how such increasingly diagonal gravity would work. Although this is a flat disk, it would feel to a runner headed toward the edge like they were fighting to climb up a steeper and steeper hill. The building foundations behind the runner reflect how you would have to build structures closer and closer to the edge so that people living in them always felt like down was at right angles to the floor, the way we feel it on our big round Earth. Now, as you approach the edge, things would get scary. Remember, this is a flat Earth, but it would feel like a sheer drop-off. What's really cool is that contrary to the don't fall off the edge fear, on a flat world, because of gravity, the scary risk would actually be falling away from the edge and rolling all the way back to the center. Once you stepped over the edge, instead of falling off into space, you'd be able to relax. It would be a nice, level place. This model, of course, neglects the fact that such a planet shape would be impossible. Anything as massive as the Earth, shaped like a flat disk, would, under its own gravity, naturally collapse back into a ball. This is why in outer space, everything more than a few hundred miles in diameter is round. Or so we've been told. What if gravity isn't real? What if the Earth is in fact flat and science has been wrong all along? It's a misconception that Christopher Columbus discovered that the Earth is round. Virtually every scholar and major religion in the West accepted Earth's rotundity since at least the time of the ancient Greeks, who, for instance, had noticed that boats disappear bottom first when sailing away, and as you walk north and south, stars pop into and out of view. The misconception that only a few hundred years ago lots and lots of people believed the Earth was flat likely began in the modern era as a sort of insult, well, your people recently thought the Earth was flat, so why should we believe you now? The smear was repeated and published so often it became accepted as historical fact. Flat earther became synonymous with anti-science. It might seem flat over short distances, but over longer ones, well, the Earth is pretty darn curvy. The Verrazano Narrows Bridge, connecting Staten Island and Brooklyn, had to be designed with Earth's roundness in mind. Its two towers, separated by 1,300 meters and perfectly vertical, are nonetheless 41 millimeters further apart at the top than at the bottom because of Earth's curvature. In the 3rd century BC, Eratosthenes measured the differences between shadows cast by poles in Syene and Alexandria to calculate
more than 2,000 years before rockets and space travel the circumference of the entire globular Earth, with, for the time, impressive accuracy. Word got around that the Earth was a round shape after that. But in 1906, Wilbur Glenn Vsause became head of a slightly bizarre religious sect that pretty much ran the city of Zion, Illinois. Vsause believed that the Earth was actually flat, and he enforced flat Earth teachings in schools in Zion. He also enforced that belief on really anyone who entered the city. Vsause believed not only that the Earth was flat, but that the sun was only a few thousand miles away from Earth, not 93 million. He also believed that the sun was only 32 miles across, not 860,000. He sounds crazy. Or does he? You see, the same phenomenon Eratosthenes measured could be explained by a flat Earth if the sun were only a few thousand miles away and 32 miles across. The math would work out the same. Today, with the power of the internet, modern-day flat earthers have picked up where Vsause left off. They have quite good explanations for any evidence you throw at them that the Earth is round. Circumnavigation is really just a flat circle path. The round shadow Earth casts on the moon during a lunar eclipse could also be made by a flat disk. Time zones are caused by a spotlight sun. And remember how gravity would be totally different on a disc-shaped planet? Well, they argue that gravity as we know it simply doesn't exist. The flat disk of Earth is merely accelerating up at 9.8 meters per second. As for all of the photos and video evidence we now have that the Earth is round thanks to space exploration, well, all of that material is completely fabricated. A hoax perpetrated by Big Globe. Space agencies, airlines, globe manufacturers, they are reaping the rewards of our ignorant belief that the Earth is actually round. They know, of course, that it's flat, and they're hiding that truth from us. Is it merely a coincidence that the logo used by the Flat Earth Society is a projection of Earth centered on the North Pole and also happens to be the projection used by the United Nations? Are these people for real? Probably not most of them, but this is the crux of Poe's law. An adage that states that at their extremes, parody of extremism and sincere extremism are difficult to distinguish. Although clever, flat Earth theories are predominantly ad hoc explanations, excuses made up on the spot that only address one issue and don't fit all the evidence. Science, of course, rejects a theory if a better one fits more of our observations, but why the egotistical obsession with our observations? A cosmic ray particle could use the very same scientific method we use and conclude that the Earth was in fact flat. You see, at speeds near the speed of light, time slows down and lengths contract. One way we know this is that unstable muons created in the upper atmosphere by the collision of cosmic rays with the atmosphere should mostly decay before reaching Earth's surface. But yet, we detect a lot of them down here, because their crazy fast speed literally means that from our perspective, their physics runs according to a slower clock. And to them, the distance they have to cover to the surface during their short lives is, from their perspective, much, much shorter than it appears to us. If you were a cosmic ray proton traveling at 99.99999999991% the speed of light, Earth would appear to be only 17 meters thick in the direction you traveled. So Earth is flat to them, but round to us. It is ball-shaped to some observers and flat to others. There doesn't appear to be a single most correctest in all circumstances answer. Susan Hack compares knowledge to a crossword puzzle. New answers interweave with old ones. They all reinforce one another. The clues are the questions we ask, and the way the answers fall into a predetermined grid, well, that's our confidence that we're on the right track. But that doesn't mean that one day there will be a finished puzzle a complete answer, recall the New York Times' famous 1996 crossword puzzle that came out the day before the US election between Bill Clinton and Bob Dole. The clue for 39 across was pretty crazy. You seemed to need to be able to tell the future to answer it correctly. It simply said, lead story in tomorrow's newspaper. Blank elected. Well, that blank could be Clinton or Bob Dole. And who's to say which one until tomorrow? There's no way to know. But as it turned out, the answer was Clinton or Bob Dole. No matter which you wrote in, all the other clues fit. For instance, a black Halloween animal could either be a cat or a bat. Our knowledge about the outside world might be the same. A puzzle with no answer key, just the reassurance that the answers we think we know fit together, so they're probably correct, though there's always the possibility that the answer to one clue or all of them will fundamentally not have a single definite satisfying answer. The puzzle may be playable forever. I like what Richard Feynman says about this. Some people say, how can you live without knowing? I do not know what they mean. I always live without knowing. That is easy. How you get to know is what I want to know. You know? And as always, thanks for watching.
My problem is, I have more than one emotion.
Check this out.
Son. Hey, Vsause, Michael here. This appears blue. This appears yellow, and this appears green. Those of us with normal color vision can probably agree, but that doesn't change the fact that color is an illusion. Color as we know it does not exist in the outside world, beyond us, like gravity or protons do. Instead, color is created inside our heads. Our brains convert a certain range of the electromagnetic spectrum into color. I can measure the wavelength of radiation, but I can't measure or observe the experience of a color inside your mind. So, how do I know that when you and me look at a strawberry, and in my brain this perception occurs, which I call red, that in your brain a perception like this doesn't occur, which you have of course also learned to call red. We both call it red, we communicate effectively, and walk away, never knowing just how different each of our internal experiences really were. Of course, we already know that not everybody sees color in exactly the same way. One example would be color blindness. But we can diagnose and discuss these differences because people with the conditions fail to see things that most of us can. Conceivably, though, there could be ways of seeing that we use that cause colors to look differently in different people's minds without altering their performances on any tests we could come up with. Of course, if that were the case, wouldn't some people think other colors looked better than others, or that some colors were more complementary of others? Well, yeah, but doesn't that already happen? This matters because it shows how fundamentally, in terms of our perceptions, we are all alone in our minds. Let's say I met an alien from a faraway solar system who, lucky enough, could speak English, but had never and could never feel pain. I could explain to the alien that pain is sent through A delta and C fibers to the spinal cord. The alien could learn every single cell and pathway and process and chemical involved in the feeling of pain. The alien could pass a biology exam about pain and believe that pain to us generally is a bad thing. But no matter how much he learned, the alien would never actually feel pain. Philosophers call these ineffable, raw feelings qualia. And our inability to connect physical phenomenon to these raw feelings, our inability to explain and share our own internal qualia, is known as the explanatory gap. This gap is confronted when describing color to someone who has been blind their entire life. Tommy Edison has never been able to see. He has a YouTube channel where he describes what being blind is like. It's an amazing channel. In one video, he talks about colors and how strange and foreign of a concept it seems to him. Sighted people try to explain, for instance, that red is hot and blue is cold. But to someone who has never seen a single color, that just seems weird. And as he explains, it has never caused him to finally see a color. Some philosophers, like Daniel Dennett, argue that qualia may be private and ineffable simply because of a failure of our own language, not because they are necessarily always going to be impossible to share. There may be an alien race that communicates in a language that causes colors to appear in your brain without your retina having to be involved at all, or without you having to have ever needed to actually see the color yourself. Perhaps even in English, he says, given millions and billions of words used in just the right way, it may be possible to adequately describe a color such that a blind person could see it for the first time. Or you could figure out that once and for all, yes, or no, in fact, you and your friend do not see the same red. But for now, it remains the case that we have no way of knowing if my red is the same as your red. Maybe one day our language will allow us to share and find out. Or maybe it never will. I know it's frustrating to not have an answer, but the mere fact that you guys can ask me about my internal experiences, and the mere fact that I can ask my friends, and we can all collectively wonder at the concept of qualia, is quite incredible, and also quite human. Animals can do all sorts of clever things that we do. They can use tools, problem solve, communicate, cooperate, exhibit curiosity, plan for the future. And although we can't know for sure, many animals certainly act as if they feel emotions, loneliness, fear, joy. Apes have even been taught to use language to talk to us humans. It's a sort of sign language that they've used to do everything from answer questions to express emotion or even produce novel thoughts. Unlike any other animal, these apes are able to understand language and form responses at about the level of a 2.5-year-old human child. But there's something that no signing ape has ever done. No ape has ever asked a question. Joseph Jordania's Who Asked the First Question is a great read on this topic, and it's available for free online. For as long as we have been able to use sign language to communicate with apes, they have never wondered out loud about anything that we might know that they don't. Of course, this does not mean that apes and plenty of other animals aren't curious. They obviously are. But what it suggests is that they lack a theory of mind, an understanding that other people have separate minds, that they have knowledge, access to information that you might not have. Even us humans aren't born with a theory of mind, and there's a famous experiment to test when a human child first develops a theory of mind. It is called the Sally-Ann test. During the test, researchers tell children a story about Sally and Ann. Sally and Ann have a box and a basket in their room. They also happen to have a delicious cookie. Now Sally takes the cookie and puts it inside the box, and then Sally leaves the room. While Sally is gone, Ann comes over to the box, takes the cookie out, and puts the cookie inside the basket. Now, when Sally comes back, the researchers ask the children, where will Sally look for the cookie? Obviously, Sally will look in the box. That's where she left it. She has no way of knowing what Anne did while she was gone. But until the age of about 4, children will insist that Sally will check the basket, because after all, that's where the cookie is. The child saw Anne move the cookie, so why wouldn't Sally also know? Young children fail to realize that Sally's mental representation of the situation, her access to information, can be different than their own. And apes who know sign language but never ask us questions are doing the same thing. They're failing to recognize that other individuals have similar cognitive abilities and can be used as sources of information. So, we are all alone with our perceptions. We are alone in our own minds. We can both agree that chocolate tastes good, but I cannot climb into your consciousness and experience what chocolate tastes like to you. I can never know if my red looks the same as your red, but I can ask. So stay human. Stay curious and let the entire world know that you are. And as always, thanks for watching.
Please tell me you weren't laughing just now. What if you get sent out on the phone making the wrong face?
Dad, I'll make the right face. Then I would finally fit in.
Sweetie, you're so handsome when you make that face. I think he's ready, Mel.
Hey, Vsause, Michael here. There's a famous way to seemingly create chocolate out of nothing. Maybe you've seen it before. This chocolate bar is 4 squares by 8 squares. But if you cut it like this, and then like this, and finally like this, you can rearrange the pieces like so and wind up with the same 4 by 8 bar, but with a leftover piece apparently created out of thin air. There's a popular animation of this illusion as well. I call it an illusion because it's just that, fake. In reality, the final bar is a bit smaller. It contains this much less chocolate. Each square along the cut is shorter than it was in the original, but the cut makes it difficult to notice right away. The animation is extra misleading because it tries to cover up its deception. The lost height of each square is surreptitiously added in, while the piece moves to make it hard to notice. I mean, come on. Obviously, you cannot cut up a chocolate bar and rearrange the pieces into more than you started with. Or can you? One of the strangest theorems in modern mathematics is the Banach-Tarski paradox. It proves that there is in fact a way to take an object and separate it into 5 different pieces. And then, with those 5 pieces, simply rearrange them, no stretching required, into 2 exact copies of the original item. Same density, same size, same everything. Seriously, to dive into the mind blow that it is and the way it fundamentally questions math and ourselves, we have to start by asking a few questions. First, what is infinity? A number? I mean, it's nowhere on the number line, but we often say things like, there's an infinite number of blah blah blah. And as far as we know, infinity could be real. The universe may be infinite in size and flat, extending out forever and ever without end, beyond even the part we can't observe or ever hope to observe. That's exactly what infinity is. Not a number per se, but rather a size. The size of something that doesn't end. Infinity is not the biggest number. Instead, it is how many numbers there are. But there are different sizes of infinity. The smallest type of infinity is countable infinity, the number of hours in forever. It's also the number of whole numbers that there are, natural numbers, the numbers we use when counting things like 1, 2, 3, 4, 5, 6, and so on. Sets like these are unending, but they are countable. Countable means that you can count them from one element to any other in a finite amount of time. Even if that finite amount of time is longer than you will live, or the universe will exist for, it's still finite. Uncountable infinity, on the other hand, is literally bigger. Too big to even count. The number of real numbers that there are, not just whole numbers, but all numbers, is uncountably infinite. You literally cannot count even from 0 to 1 in a finite amount of time by naming every real number in between. I mean, where do you even start? 0, okay, but what comes next? 0.000000. Eventually, we would imagine a 1 going somewhere at the end, but there is no end. We could always add another 0. Uncountability makes this set so much larger than the set of all whole numbers that even between 0 and 1, there are more numbers than there are whole numbers on the entire endless number line. Derek Cantor's famous diagonal argument helps illustrate this. Imagine listing every number between 0 and 1. Since they are uncountable and can't be listed in order, let's imagine randomly generating them forever with no repeats. Each number we generate can be paired with a whole number. If there's a 1-to-1 correspondence between the two, that is, if we can match one whole number to each real number on our list, that would mean that countable and uncountable sets are the same size. But we can't do that. Even though this list goes on forever, forever isn't enough. Watch this. If we go diagonally down our endless list of real numbers and take the first decimal of the first number and the second of the second number, the third of the third, and so on, and add 1 to each, subtracting 1 if it happens to be a 9, we can generate a new real number that is obviously between 0 and 1, but since we've defined it to be different from every number on our endless list in at least one place, it's clearly not contained in the list. In other words, we've used up every single whole number, the entire infinity of them, and yet we can still come up with more real numbers. Here's something else that is true but counterintuitive. There are the same number of even numbers as there are even and odd numbers. At first, that sounds ridiculous. Clearly, there are only half as many even numbers as all whole numbers, but that intuition is wrong. The set of all whole numbers is denser, but every even number can be matched with a whole number. You will never run out of members of either set, so this 1-to-1 correspondence shows that both sets are the same size. In other words, infinity divided by 2 is still infinity. Infinity plus 1 is also infinity. A good illustration of this is Hilbert's paradox of the Grand Hotel. Imagine a hotel with a countably infinite number of rooms. But now, imagine that there is a person booked into every single room. Seemingly, it's fully booked, right? No. Infinite sets go against common sense. You see, if a new guest shows up and wants a room, all the hotel has to do is move the guest in room number 1 to room number 2, and the guest in room 2 to room 3, and 3 to 4, and 4 to 5, and so on. Because the number of rooms is never ending, we cannot run out of rooms. Infinity minus 1 is also infinity again. If one guest leaves the hotel, we can shift every guest the other way. Guest 2 goes to room 1, 3 to 2, 4 to 3, and so on. Because we have an infinite amount of guests, that is a never-ending supply of them, no room will be left empty. As it turns out, you can subtract any finite number from infinity and still be left with infinity. It doesn't care. It's unending. Banach-Tarski hasn't left our sights yet. All of this is related. We are now ready to move on to shapes. Hilbert's hotel can be applied to a circle. Points around the circumference can be thought of as guests. If we remove one point from the circle, that point is gone, right? Infinity tells us it doesn't matter. The circumference of a circle is irrational. It's the radius times 2 pi. So if we mark off points beginning from the hole, every radius length along the circumference going clockwise, we will never land on the same point twice. Ever. We can count off each point we mark with a whole number. So this set is never ending, but countable, just like guests in rooms in Hilbert's hotel. And like those guests, even though one has checked out, we can just shift the rest. Move them counterclockwise, and every room will be filled. Point 1 moves to fill in the hole, point 2 fills in the place where point 1 used to be, 3 fills in 2, and so on. Since we have an unending supply of numbered points, no hole will be left unfilled. The missing point is forgotten. We apparently never needed it to be complete. There's one last neato consequence of infinity we should discuss before tackling Banach-Tarski. Ian Stewart famously proposed a brilliant dictionary, one that he called the Hyperwebster. The Hyperwebster lists every single possible word of any length formed from the 26 letters in the English alphabet. It begins with A, followed by AA, then AAA, then AAAA, and after an infinite number of those, AB, then ABA, then ABAA, ABAAA, and so on until Z, ZA, ZAA, etc., until the final entry, an infinite sequence of Z's. Such a dictionary would contain every single word. Nay, every single thought, definition, description, truth, lie, name, story. What happened to Amelia Earhart would be in that dictionary, as well as every single thing that didn't happen to Amelia Earhart. Everything that could be said using our alphabet. Obviously, it would be huge, but the company publishing it might realize that they could take a shortcut. If they put all the words that begin with A in a volume titled A, they wouldn't have to print the initial A. Readers would know to just add the A because it's the A volume. By removing the initial A, the publisher is left with every A word sans the first A, which has surprisingly become every possible word. Just one of the 26 volumes has been decomposed into the entire thing. It is now that we're ready to investigate this video's titular paradox. What if we turned an object, a 3D thing, into a hyperwebster? Could we decompose pieces of it into the whole thing? Yes. The first thing we need to do is give every single point on the surface of the sphere one name and one name only. A good way to do this is to name them after how they can be reached by a given starting point. If we move this starting point across the surface of the sphere in steps that are just the right length, no matter how many times or in what direction we rotate, so long as we never backtrack, it will never wind up in the same place twice. We only need to rotate in 4 directions to achieve this paradox: up, down, left, and right, around 2 perpendicular axes. We are going to need every single possible sequence that can be made of any finite length out of just these 4 rotations. That means we will need left, right, up, and down, as well as left, 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 up, left, down, but of course not left, right, because, well, that's backtracking. Going left and then right means you're the same as you were before you did anything. So no left rights, no right lefts, and no up downs, and no down ups. Also, notice that I'm writing the rotations in order right to left, so the final rotation is the leftmost letter. That will be important later on. Anyway, a list of all possible sequences of allowed rotations that are finite in length is, well, huge. uncountably infinite, in fact. But if we apply each one of them to a starting point, in green here, and then name the point we land on after the sequence that brought us there, we can name a countably infinite set of points on the surface. Let's look at how, say, these 4 strings on our list would work. Right, up, left. Okay, rotating the starting point this way takes us here. Let's color code the point based on the final rotation in its string. In this case, it's left, and for that we will use purple. Next up, down, down. That sequence takes us here. We name the point DD and color it blue since we ended with a down rotation. RDR, that will be this point's name, takes us here, and for a final right rotation, let's use red. Finally, for a sequence that ends with up, let's color code the point orange. Now, if we imagine completing this process for every single sequence, we will have a countably infinite number of points named and color coded. That's great, but not enough. There are an uncountably infinite number of points on a sphere's surface. But no worries, we can just pick a point we missed, any point, and color it green, making it a new starting point, and then run every sequence from here. After doing this, to an uncountably infinite number of starting points, we will have indeed named and colored every single point on the surface just once. With the exception of poles. Every sequence has 2 poles of rotation, locations on the sphere that come back to exactly where they started. For any sequence of right or left rotations, the poles are the north and south poles. The problem with poles like these is that more than one sequence can lead us to them. They can be named more than once, and be colored in more than one color. For example, if you follow some other sequence to the north or south pole, any subsequent rights or lefts will be equally valid names. In order to deal with this, we're going to just count them out of the normal scheme and color them all yellow. Every sequence has 2, so there are a countably infinite amount of them. Now, with every point on the sphere given just one name and just one of 6 colors, we are ready to take the entire sphere apart. Every point on the surface corresponds to a unique line of points below it all the way to the center point, and we will be dragging every point's line along with it. The lone center point we will set aside. Okay, first we cut out and extract all the yellow poles, the green starting points, the orange up points, the blue down points, and the red and purple left and right points. That's the entire sphere. With just these pieces, you can build the whole thing. But take a look at the left piece. It is defined by being a piece composed of every point accessed via a sequence ending with a left rotation. If we rotate this piece right, that's the same as adding an R to every point's name. But left and then right is a backtrack. They cancel each other out. And look what happens when we reduce them away. The set becomes the same as a set of all points with names that end with L, but also U, D, and every point reached with no rotation. That's the full set of starting points. We have turned less than a quarter of the sphere into nearly 3/4 just by rotating it. We added nothing. It's like the hyperwebster. If we add the right piece and the poles of rotation in the center point, well, we've got the entire sphere again, but with stuff left over. To make a second copy, let's rotate the up piece down. The down-ups cancel because, well, it's the same as going nowhere, and we're left with a set of all starting points, the entire up piece, the right piece, and the left piece. But there's a problem here. We don't need this extra set of starting points. We still haven't used the original ones. No worries, let's just start over. We can just move everything from the up piece that turns into a starting point when rotated down. That means every point whose final rotation is up. Let's put them in the down piece. Of course, after rotating, points named UU will just turn into points named U, and that would give us a copy here and here. So as it turns out, we need to move all points with any name that is just a string of U's. We will put them in the down piece and rotate the up piece down, which makes it congruent to the up, right, and left pieces. Add in the down piece along with some up and the starting point piece, and, well, we're almost done. The poles of rotation and center are missing from this copy, but no worries. There's a countably infinite number of holes where the poles of rotation used to be, which means there is some pole around which we can rotate this sphere such that every pole hole orbits around without hitting another. Well, this is just a bunch of circles with one point missing. We fill them each like we did earlier, and we do the same for the center point. Imagine a circle that contains it inside the sphere and just fill in from infinity. And look what we've done. We have taken one sphere and turned it into two identical spheres without adding anything. 1 + 1 = 1. That took a while to go through, but the implications are huge. And mathematicians, scientists, and philosophers are still debating them. Could such a process happen in the real world? I mean, it can happen mathematically, and math allows us to abstractly predict and describe a lot of things in the real world with amazing accuracy. But does the Banach-Tarski paradox take it too far? Is it a place where math and physics separate? We still don't know. History is full of examples of mathematical concepts developed in the abstract that we did not think would ever apply to the real world for years, decades, centuries, until eventually science caught up and realized they were totally applicable and useful. The Banach-Tarski paradox could actually happen in our real world. The only catch, of course, is that the 5 pieces you cut your object into aren't simple shapes. They must be infinitely complex and detailed. That's not possible to do in the real world, where measurements can only get so small and there's only a finite amount of time to do anything. But math says it's theoretically valid, and some scientists think it may be physically valid too. There have been a number of papers published suggesting a link between Banach-Tarski and the way tiny subatomic particles can collide at high energies and turn into more particles than we began with. We are finite creatures. Our lives are small and can only scientifically consider a small part of reality. What's common for us is just a sliver of what's available. We can only see so much of the electromagnetic spectrum. We can only delve so deep into extensions of space. Common sense applies to that which we can access. But common sense is just that. Common. If total sense is what we want, we should be prepared to accept that we shouldn't call infinity weird or strange. The results we've arrived at by accepting it are valid, true within the system we use to understand, measure, predict, and order the universe. Perhaps the system still needs perfecting. But at the end of the day, history continues to show us that the universe isn't strange. We are. And as always, thanks for watching. Finally, as always, the description is full of links to learn more. There are also a number of books linked down there that really helped me wrap my mind kind of around Banach-Tarski. First of all, Leonard Wapner's The Pea and the Sun. This book is fantastic and it's full of a lot of the preliminaries needed to understand the proof that comes later. He also talks a lot about the ramifications of what Banach-Tarski and their theorem might mean for mathematics. Also, if you want to talk about math and whether it's discovered or invented, whether it really truly will map onto the universe, Yanofsky's The Outer Limits of Reason is great. This is the favorite book of mine that I've read this entire year. Another good one is E. Brian Davies' Why Beliefs Matter. This is actually Korn's favorite book, as you might be able to see there. It's delicious and full of lots of great information about the limits of what we can know, and what science is, and what mathematics is. If you love infinity and math, I cannot more highly recommend Matt Parker's Things to Make and Do in the Fourth Dimension. He is hilarious, and this book is very, very great at explaining some pretty awesome things. So keep reading, and if you're looking for something to watch, I hope you've already watched Kevin Lieber's film on Field Day. I already did a documentary about Whittier, Alaska over there. Kevin's got a great short film about putting things out on the internet and having people react to them. There's a rumor that Jake Roper might be doing something on Field Day soon. So check out mine, check out Kevin's, and subscribe to Field Day for upcoming Jake Roper action, yeah? He's actually in this room right now. Say hi, Jake.
Hi.
Thanks for filming this, by the way.
You're welcome.
Guys, I really appreciate who you all are. And as always, thanks for watching.
That's our user, Alex.
We have an incoming text. We are go for Matt.
Who, me?
What's he doing?
He's making the wrong face.
Huh?
What the heck?
Using GPS, these trails represent pizza delivery in Manhattan on a typical Friday night. And is this a frog or a horse? It's episode 52 of IMG. This lemon looks yellow to me, and it probably looks yellow to you as well, but not in the same way. You see, here in this room, this lemon is subtractively yellow. It absorbs all visible wavelengths of light except for yellow light, which it reflects onto my retina. But the screen that you are using to watch this video doesn't produce yellow light at all. In fact, it can only produce red, blue, or green light. The really cool but kind of disturbing thing about this is that here in the room, I am actually seeing real yellow light, but you are seeing fake yellow. Absolutely no yellow is coming off of your screen and falling on your retina. But it still looks yellow because it's quite easy to lie to the brain. Our retinas contain 3 different types of cone cells that are receptive to color, and each one is best suited to detect a certain color. One is great for blue, the other is great for green, and the third is great for red. Notice that there's no individual cell looking for yellow. So the way we actually see yellow happens like this. The wavelength of yellow light falls between the wavelengths of red and green. And so when an object reflects yellow light onto your retina, both the green and the red cones are slightly activated, which your brain notices and says, well, that's what happens when something's yellow, so it must be yellow. All a computer monitor or a mobile phone screen has to do to make you think you're seeing yellow is send a little bit of red and a little bit of green light at you. As long as the pixels and the little sub-pixels on them are small enough that you can't distinguish them individually, your brain will just say, well, I'm receiving some red and some green. That's what yellow things do. It must be yellow. Even though it actually is not. Lemons can also produce electricity. A little bit of zinc, a little bit of copper, and boom, you're moving electrons around. But not that many. I mean, the current and voltage are quite low. You could run an LCD, but even a potato could do that. If you wanted to run a flashlight bulb, that would take 3,000 lemons. And if you wanted to run a halogen bulb, well, that would take 37,000 lemons. But artist Caleb Sharland doesn't care. He spent 11 hours hammering nails into 300 living apples hanging on trees. By connecting them to a household lamp, he was able to make it glow just dimly enough to capture this image with a 4-hour exposure. Less alive and more frightening are Steve Shaheen's sculptures, little dudes with bulb heads desperately trying to plug themselves in. Merv Karaman's Revitalizer never dies. It's a light bulb surrounded by wax. Now the wax melts because of the light bulb's heat and drips into a special container into all kinds of weird new shapes. But whenever you want, you can just flip it so that the new cooled wax is at the top. But my favorite is the Vsause wooden light bulb. It looks like a solid block of wood, but it's actually hollow and chipped to a nearly paper-thin width. When you turn it on, you can see the light coming from inside. Combos. Artist Tang Yo Hung blew my mind this week. We've got clear days and smoke, boats and crocs, whales and hearts, pie bike, brains and boxing gloves, day and night. But don't be scared, you can always paint yourself some light, or just swing on some light. Okay, let's frame it this way: climbing wall. This fitness club in Japan uses frames and other pretty interior elements to create a decidedly less rugged climbing wall. But let's get simple, like minimal. Thanks to Lego, here are their bricks arranged to represent famous characters. Enjoy. Now for some art. Illusions. Here's a cute couple, but can you see in this very same image the baby they will soon have? Or how about these zebras? There's a lion hiding amongst them. Can you find it? Billboards can be clever, but here's a great one that makes it look like someone is pushing out a section of the building. But how many of you will remember seeing it? If we assume that you don't remember experiencing major cultural events before you're 5 or 6 years old, that means that every year there are fewer and fewer people alive who remember experiencing recent historical events. XKCD made this amazing chart to show when, in the future, the majority, more than half of living Americans will not remember being alive when certain things happened. For instance, he calculated using data from the US Census Bureau that 2012, this very year, is the first year in American history since in which fewer than half of living Americans remember being alive in the 1970s. By 2041, most of us won't remember a time when Pluto was actually called a planet. By 2043, most of us alive won't remember living during George W. Bush's presidency. And by 2047, more than half of living Americans will not have been alive to have remembered anything that you did today. Like when you made that funny face in the yearbook. No, that funny face. If you're not following Vsause, you are missing out on daily Vsause content, most of which never makes it to a video. So go follow us on Twitter, and I'm gonna leave you with another combo. A tessellation while you listen to Jake Chudnow's Flan. He made a music video for this song over on his channel, so check that out, and as always, thanks for watching.
Welcome to the Loser Lounge, where the emojis who never get used hang out.
What's up, High Five?
I'm an emoji. I've got to have some sort of purpose here.
I'm gonna help you. We need to get off the phone and find the source code.
Then I can fit in.
Let's roll! Bye, Felicia.
Hey, Vsause Michael here, and today we are going to go inside a black hole. It's not going to be comfortable, but it will be pretty fun. Now, first things first, mathematically speaking, anything could become a black hole if you were to compress it into a small enough space. That's right, you, me, this camera, everything in the universe has what is known as a Schwarzschild radius, a tiny, tiny amount of space that, were you to collapse the entire mass of the object into, its density would be so great that its gravitational pull would be so great that not even light could escape from it. You would have a black hole. If you were to compress Mount Everest into something smaller than a nanometer, you would have a black hole. And if you were to compress the entire Earth down to the size of a peanut, you would have a black hole. But fortunately for us, there is no known way to compress Everest or Earth in that fashion. But a star, many, many, many times larger than our own sun, has a much larger Schwarzschild radius, and when it runs out of fuel and can no longer keep itself hot enough, it collapses to a single infinitesimally small point known as a singularity. Its density will be infinite, and so its gravitational pull will be so strong that nothing can escape, not even light. But enough about ways black holes form, let's jump into one. First question, what would it look like from the outside? Well, we know that gravitational fields bend space and time. Stars behind our sun will actually appear to be in slightly different locations from Earth because the sun's gravitational field bends the light coming from those stars. When it comes to the gravitational fields of larger objects like entire galaxies, or for that matter a black hole, the effect is even nuttier. Light coming from objects behind them is significantly distorted, producing smears and smudges. As seen from Earth, the blue galaxy behind this red galaxy is completely distorted like a funhouse mirror, so rather than appearing as it really should, it looks to us like a ring, a smudge all the way around the red galaxy. This is known as gravitational lensing. Now take a look at this simulation of a black hole with a galaxy millions of light years behind it. The galaxy is not really in danger of the black hole's suck, but the light coming off of that galaxy certainly is. Watch as the galaxy passes behind the black hole, and its light is contorted, twisted, and distorted. Now here's a really fun demonstration. What if the Earth were to orbit around a black hole? Looking from the outside, the Earth would look normal at first, but as soon as it passed behind the black hole's gravitational field would warp the light reflecting off the Earth, producing this. For the sake of simplicity, let's jump into a simple black hole, one that doesn't have a charge and isn't moving, and also isn't already sucking up a bunch of matter, so it's just there on its own. As we approach, the distortion of the sky grows greater and greater. A larger and larger portion of our field of view looking forward into the black hole will be filled with darkness. At this point, where half of our field of view has been swallowed up in darkness, we have reached the photon sphere. At this point, light is not going to necessarily get sucked into the black hole, but it doesn't necessarily leave it either. Instead, at this magical point in space, light, photons, can actually orbit the black hole. If you were to stop here for a moment and look to the side, you could theoretically see the back of your own head, because light reflecting off the back of your head would travel all the way around the sphere of the black hole right back to your face. A gravitational field not only warps space, it also warps time. Now, for most intents and purposes here on Earth, we never have to worry about that. But near a black hole, gravity would be so strong that an observer standing, watching you jump into the hole, would see something quite strange. They wouldn't see you get sucked quickly into the hole. Instead, they would see your approach become slower and slower and slower until you reached a point known as the event horizon. This is a point in space where, once crossed, there's no going back. It is at that point that light can no longer escape. And so to a person watching you fall into the hole, that would be where your journey ended. You would seem almost frozen in space, the light coming off your body becoming increasingly red-shifted until you simply faded into nothingness. They would never see you cross the event horizon. But for you, of course, everything would seem fine and dandy. You would continue past that horizon to your now inevitable death. As you continue to approach the black hole's singularity, your view of the entire universe would get compressed into a smaller and smaller point in space behind you. If the black hole we're jumping into is large enough, things might actually be quite comfortable at that event horizon. We'll know that we're never going to escape and that our lives are pretty much over, but it might take us hours to actually reach a point where things started to hurt. Why would they hurt? Well, the closer you get to the singularity, the more significant the difference in gravitational pull is across space. And so parts of me that are closer to the singularity would be pulled more strongly than parts that were facing away, and my entire body would be stretched toward the singularity. The effect would be so incredible, scientists don't usually call it stretching, they call it spaghettification. Once you reached this point, you would be dead. Your molecules would be violently ripped and stretched apart, and when they got to the singularity, well, we don't really know what would happen. Perhaps they would completely disappear in violation of all the laws of physics, or maybe they would reappear elsewhere in the universe. It's believed that a moving or spinning black hole might actually create what is known as a wormhole, a way of transitioning across space faster than light. Not in any way that violates the laws of science, but in a way that takes advantage of the universe's dimensions. For instance, if I wanted to get from this point to this point, I'd have to travel the distance. But theoretically, a wormhole would do something really crazy. For instance, this. Now, the 2 points are right next to each other and I can travel between them almost instantaneously. But again, this is all theoretical. Luckily, we do have a possible way of analyzing black holes right here on Earth. Enter the dumb hole. Just as a black hole does not permit light to escape, a dumb hole is an acoustic black hole. It won't allow sound to escape. It doesn't have to be nearly as powerful, and scientists have been able to create dumb holes in laboratories using special fluids traveling at the speed of sound. A lot of progress still needs to be made in the world of acoustic black holes, but we may be able to learn an amazing amount of information about how black holes work by looking at how sound is treated in a dumb hole. Now here's another good question. What would it look like to travel at the speed of light, say, toward the sun? Well, surprisingly, you wouldn't just see the sun immediately rush up toward you. No. In fact, initially, it would look almost as if the sun were receding away from you. Why? Because your field of view would vastly increase in size. You would be able to see stuff almost behind you, and here's why. As you sit there, not moving yet, looking at the sun, there's light coming from stuff behind you. But if you travel the speed of light, you will actually reach that light coming from things behind you. As you reached light speed, your field of view would expand like this, concentrating the stuff in the middle. But where are you in the universe? Or here's a better question, where is the center of the universe? Well, this might sound crazy, but it's everywhere. This is known as the cosmological principle. No matter where you are in the universe, everything else will seem to be moving away from you, expanding at the same rate. The universe is expanding, but not like a balloon getting bigger with all the people inside it. Instead, it's as if we are the surface of a balloon. If you were to put a bunch of dots on a balloon and then blow it up, all of the dots would move away from each other at the same rate. And on the surface of the balloon, there is no center. Take a look at these two layers. They are exactly similar, except the top layer represents a 5% expansion of the bottom layer. Let's say that you live on one of these dots, and you want to measure where everything's moving away from. Well, watch what happens when I line up a dot in the past and the present. Boom. It looks like the center of the expansion. I can do this with any dot. As soon as I choose a dot to be the frame of reference, it immediately becomes the center of the expansion. So while dying in a black hole would be lonely and scary and morbid, when you look up into the sky, think instead about this. No matter where you are or who you are or what your friends or your parents tell you, you really scientifically are the center of the universe. Finally, what if our universe was a Googleplex meters across? It is nowhere near that large, but if it was, it would be so voluminous that statistically, it would be nearly impossible for there not to be an exact copy of you somewhere else out there in the universe. To see why, I highly suggest that you click right there and check out Brady Heron's new channel, Numberphile. It's part of the YouTube original channels, and I've worked with these guys before. They're amazing. They're my favorite kind of geeks. So check out that video, watch their other stuff, and if you like math, I highly suggest that you subscribe. And as always, thanks for watching.
First, we have to get through this firewall. What's Alex's girlfriend's name again?
It was Tina.
Access denied.
Karen. Sarah. I want to say Lupita, but that doesn't feel right now I'm saying it out loud.
Hey, Vsause, Michael here, and today we are going to talk about color.
Green, 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 green.
Hold on, let me just pink this up. Yellow.
Michael, aren't you going to come to the concert this evening?
I read about that. There's going to be a lot of purple there.
I didn't tell you about this earlier?
Well, look, I have to go brown town first, but I'll be white, black. Colors.
Did you know that the human eye can differentiate 10 million different colors?
But what color is a mirror? You might say silver because mirrors are often illustrated that way. And to be sure, they are made out of silver or silvery things like aluminum. But a mirror, in reality, is whatever color you point it at. In this green room, the mirror is green. And if you look inside a mirror, it becomes you-colored. An object is whatever color it doesn't absorb. These sticky notes are orange because when hit with typical white light, they absorb every other wavelength of visible light except for orange, which they diffuse into your eyeballs. But a perfect mirror reflects all colors equally. So in a way, you could say that a mirror is white. Except a mirror doesn't reflect colors in the same way that pigment does. A mirror reflects incoming light in a single outgoing direction. Specular reflection, not diffuse. This kind of reflection creates an image of the very thing in front of the mirror. So as bad astronomy jokes, a mirror is more of a smart white. But wait a second. That is a perfect mirror, and we live in the real world where there are no perfect mirrors. Every mirror absorbs a little bit of light. Not enough that it matters, I mean, looks pretty clear to me, but when you take a look at the spectrum of light reflected by a typical mirror, you will find that it best reflects light within the 510 nanometer range, which we perceive as green light. So technically, a mirror is a tiny, tiny, tiny bit green. You may have noticed this yourself when investigating a mirror tunnel. This happens when two mirrors face each other, reflecting the same scene back and forth and back and forth and back and forth. With each new reflection, a little bit more visual light is lost, but green least of all. That's why the reflection way down the tunnel is dimmer and greener. So maybe real-world mirrors aren't smart white, they're actually kind of green, but we should talk about white.
En español, white es blanco.
En français, white se dit blanc.
And in English, we have a word that comes from the same root, black, which is the opposite of white. How did that happen? Well, it turns out that all of those words come from the same ancient Proto-Indo-European root word, black, which meant shine, burn, flash. Some languages took it to mean the brightness of the flash, white, while others took it to mean what's left behind, the burned black darkness. If you have blue eyes, your eyes aren't actually blue in the sense that the molecules inside them are absorbing all other wavelengths of visible light and diffusing the blue. No, no, no. Instead, your eyes are blue for the same reason that the sky is blue, interference. In our sky, light from the sun encounters molecules of air, and because of the size of those molecules, light of longer wavelengths can slip on by, but shorter wavelengths crash into the particles, like blue light, and scatter, which is why we see blue when we look at the sky away from the sun. Without the air molecules, that space would just be black. And when direct sunlight has to travel through a lot of air, almost all the colors get scattered out except for the longest wavelengths, the red, which is what gives a sunrise and a sunset their color. The iris of your eyeball contains a hazy layer where light can be scattered just like the sky. Through a similar but slightly different process, shorter wavelengths are scattered more, making your eyes look blue. Unless, of course, you have some melanin in that iris, in which case your eyes are going to be green, hazel, or brown. Enjoy those colors, and as always, thanks for watching.
think you're pretty cool just the way you are.
Nobody leaves the phone! Delete them!
My feelings are huge. Maybe I'm meant to have more than just one emotion. Where am I?
Candy Crush.
Hey, Vsause, Michael here, and what if every single person on Earth jumped at the exact same time? Could it cause an earthquake, or would we not even be able to tell? Well, first things first, let's talk about the Earth's rotation. The Earth spins, it's why we have night and day, and it spins quickly. At the equator, the Earth is spinning at more than 1,000 miles per hour. Now, a spinning ice skater can speed up by moving mass closer to the center, and the Earth is no different. In fact, if you get down on the ground right now and move your mass closer to Earth's center, technically, you will speed up Earth's rotation, making this day shorter. Now, the change that you would make to the Earth's rotation is way smaller than we could even measure, but it is calculatable, and the impact can be quite impressive when you talk about redistributing more mass than just one person. For instance, last year, the earthquake in Japan redistributed so much of Earth's mass towards the center that every day since then has been 1.8 microseconds shorter. But that was a giant geological event. What can us humans do to the Earth all on our own? I mean, there are more than 7 billion of us now. What if we all got together in one place and jumped? Well, what would that even look like? Interestingly, if you took the entire human population of Earth and had them all live in one place with the same density that people live in New York City, you could fit everyone, all of us, into the state of Texas. But that's living, not standing around in a crowd, which is how we would probably want to do the jump. If every single person alive right now on Earth stood shoulder to shoulder, you could fit all of us into the city of Los Angeles. It would be an incredible sight to behold, a mere 500 square miles containing every single person on Earth. Okay, so then we jump. What happens? Unfortunately, not much. I mean, we're all awesome people here on Earth, but our collective mass compared to the mass of the entire Earth, it's like nothing. In fact, dot physics calculated that if all of us were to get together in one location and all jump 30 centimeters into the air at the exact same time, we would push Earth away from us a tiny amount. Earth would only move away from us about 1/100th of the width of a single hydrogen atom. And here's another thing. Because we are all jumping and then going back to where we started, Earth is just going to move back to where it started. So our big jump won't be able to change Earth's position in space. But come on, 7 billion people all jumping together, that's got to be able to cause some sort of seismic activity, right?
So let's say you have a lot of people all together in one place, and you have them all jump on 1, 2, 3. Did you feel that? Well, the BBC did this with 50,000 people and discovered that 1.5 kilometers away, it only registered as a 0.6 on the Richter scale. You would need 7 million times more people than even live on Earth right now to jump at once to recreate the earthquake that recently happened in Japan. So, even though we're all awesome, compared to the size of the Earth, we're not much.
But don't get too discouraged. Our collective jump would contain a lot of energy. The Straight Dope calculated that even if only the people who lived in China got together and jumped, their jump would be the equivalent of 500 tons of TNT. Of course, 500 tons of TNT doesn't do much to an Earth that weighs 6 sextillion 588 quintillion tons. To make yourself feel more powerful, pick a card. I've got 10 of them here. Let's say you choose this one. Boom. Congratulations. We have just decimated this deck of cards. Why? Well, because technically, decimate does not mean obliterate completely. Deci, 10. It means to take away 1/10 of something. So the next time you take a quiz and don't do so well on it, you only get 10%, well, sure, that's an F. But by getting 10% of them right, you decimated that quiz. And since we've been talking about crowds, let's talk about YouTube crowds, YouTube audiences, that view count that you see at the bottom of every video, and get some perspective on it. We'll begin with Dunbar's number. It's an estimation of the maximum number of people we can have stable social relationships with at a given moment, and it's based on the size of our neocortex. These aren't just acquaintances, these are people you have social contact with, a network where you know how everyone relates to everyone else, and the number is usually given to be somewhere between 100 and 230. Which means that when a YouTube video receives more than 230 views from different people, more people have seen that video than you could ever realistically hope to know well at a given moment. If a video has more than 100,000 views from different people, more people have seen that video than you will ever meet in your life. And by meet, I mean shake hands with, learn their name, talk to them for a bit. I mean, think of it this way. You and me, we are only statistically expected to live around 28,470 days. So even if you were to meet someone, 2, 3 people every day of your life, including when you were a baby, you still wouldn't meet as many people as have seen that YouTube video with 100,000 views. But keep this in mind, even though you, or even a large group of us, can't do much to change Earth's location or rotation, we can affect it a little bit. Newton's third law guarantees this. If you weigh 150 pounds, the Earth is pulling you down with a force of 150 pounds, but you are also pulling up on the Earth with a force of 150 pounds. If you fall 3 meters, the Earth has pulled you down 3 meters, but you have also exerted a equal and opposite force on the Earth. Of course, it's a lot bigger. So if you fall 3 meters, you pull the Earth up about 1/1000th of the width of a proton, which ain't bad. So the next time you move your body, the next time you jump, Felicia, think about this. You just affected the Earth as much as it affected you. You've got that kind of power. Speaking of power, you all should go check out Geek and Sundry, Felicia's new channel. It's one of my new favorite things. And,
as always,
thanks for watching.
Divine, sweet, tasty, delicious.
Oh, I'm never eating another piece of candy ever again.
High five, don't do it. Don't you do it. It's already been in there once.
Hey, Vsause, Michael here. 93% of all the humans who have ever lived are dead. For every person alive right now, there are 15 people who are no longer alive. The Earth is dangerous, but where is the most dangerous place on Earth? Ignoring freak occurrences, where is the most persistently perilous place on the surface of our planet? Well, let's begin with temperature. Extreme heat and extreme cold can kill within hours, if not minutes. In cold environments, without clothing, the human body by itself doesn't do a very good job of maintaining a high enough temperature to live. It just takes too much work. Even when you feel comfortable and warm, nearly half of your daily caloric intake is used merely to keep your body's temperature where it should be. If you took a human and stripped them naked and put them in an environment at 0 degrees Celsius, they would die from having too cold of an internal temperature within about 20 minutes. We need warmth. But one thing we need more immediately than that is oxygen. And that brings us to the summit of Mount Everest. This place on the surface of Earth has incredibly thin air. At the top of Mount Everest, there is only 1/3 as much breathable oxygen as there is down at sea level. Climbers can endure the conditions for short periods of time if they acclimate for months. But if you were to teleport from wherever you are right now directly to the summit of Everest, you would most likely die within only 2 to 3 minutes because there isn't enough oxygen.
Death would come even more quickly if you were at the bottom of the Mariana Trench. There, you would be submerged under nearly 7 miles of water, about 11 kilometers, causing the pressure around your body to exceed 15,000 pounds per square inch. At normal swimming depths, you can always hold your breath. But that far down, with that much pressure, your lungs would collapse immediately, and without oxygen, your brain would go unconscious in 15 seconds, and you'd be dead in under 90. You would die pretty much just as quickly as someone who walked into outer space without a suit on. But falling into a molten lake of lava is probably the most spectacular way to go. Contrary to what you see in many movies, your body wouldn't just burn a little bit and slowly sink as if it were in quicksand. Instead, there would be a lot of fireworks. Hot molten lava is liquid rock, 4 times as hot as your oven can ever get. And the human body is mainly made up of water, which when exposed to that kind of heat turns into steam, explosively. There's a fantastic video right here on YouTube where a guy throws a bag of organic material containing a lot of moisture into hot lava. It doesn't just sink in, it causes a miniature eruption. I highly suggest you go watch it. But what if we want to measure danger not by how quickly you would die, but by the actual total number of fatalities caused? Well, for this, we're going to need to get much, much smaller, like microscopic. In 1918, influenza killed nearly 100 million people, which at the time was 3% of the world's entire population. But places where and when the plague has spread rapidly are even scarier. Between 1347 and 1353, a third of everybody in Europe died because of the bubonic plague, an infection caused by Yersinia pestis. It's easy to think of the plague as something from way back in the past, but it is still here. Of course, now we have antibiotics, which can help in most cases, but believe it or not, in America alone, 5 to 15 people still get the plague every year. In terms of total fatalities, however, the plague and influenza are nothing compared to the danger caused by this guy, Plasmodium. It's a microorganism that can get into our blood because of mosquito bites and causes malaria. Across the totality of human history, the number of deaths attributed to malaria is unbelievable. Researchers like Nobel laureate Baruch Blumberg have studied the history of the human genome and human migration and determined that of all the humans who have ever existed, it is likely that half died from malaria. So in terms of total fatalities across all of human history, a place where Plasmodium could enter the bloodstream because of a mosquito bite, statistically speaking, could be called the most dangerous place on Earth. But let's switch gears for a moment and talk about places that are dangerous not because of Earth or Earth's creatures, well, actually just one specific creature, us. La Orilla is a mining town in Peru where the murder rate is low but pollution is high. The town's smelter emits pollution into the air, and temperature inversions in the atmosphere above the town trap gases within, causing the town to have 85 times more arsenic in its air than is deemed safe. But that's nothing compared to Lake Karachay in Russia. It was named the most polluted spot on Earth by the World Watch Institute on Nuclear Waste. The lake contains so many radioactive pollutants that you can receive a lethal dose of radiation merely by standing for 1 hour near certain parts of the lake. The Global Peace Index ranks countries by how safe they are. It takes into account a number of factors, including crime and political corruption. The safest country, according to the index, is Iceland, and the least safe is Somalia. But for the highest murder rate, you'll have to go to Juarez, Mexico, where out of every 1 million inhabitants, each year 1,477 of them are murdered. I've always found it amazing just how many serial killers Miami seems to have on the show Dexter. But Miami is a big city, and so despite all those serial killers, its murder rate in the show is not the highest of any fictional town from a TV show. That honor goes to Cabot Cove, the town where Murder, She Wrote occurred. An analysis of Murder, She Wrote episodes revealed 274 murders, but a population in the town of only 3,500, making Cabot Cove's murder rate 1,490 per million inhabitants. Until recently, that number was unmatched by reality, but last year, the city of San Pedro Sula in Honduras reported a murder rate of 1,588 murders per million inhabitants. Let's conclude by revisiting pollution, specifically the Chernobyl accident, and a certain oxymoronic danger. For 10 days in 1986, radioactive isotopes spilled out of a blazing reactor core, forcing mass evacuations. It's more than 25 years later now, and many parts of the exclusion zone remain incredibly lethal. But without humans there, many parts of the exclusion zone have seen wildlife flourish, especially endangered species, which can go to the exclusion zone, live, reproduce, and be safe from us. We managed to ruin a place to the point at which it endangered our lives and we had to leave. And in doing so, we left parts of it a little bit safer for other forms of life. You can read more about all of these topics by following links down in the description below. Keep learning, and as always, thanks for watching.
Okay, son, what do we do after we go potty?
Should we wash our hands?
We're number 2!
Hey, Vsause. Michael here. Fear gives us life. Being afraid of the right things kept our ancestors alive. It makes sense to be afraid of poisonous insects or hungry tigers. But what about fear when there is no clear and obvious danger? For instance, a teddy bear with a full set of human teeth. Or a smile.jpg. There's something a little off about these images, too much mystery and strangeness, but no obvious threat the way there is with a gun or a falling rock, but yet they still incite fear because they are creepy. But why? What gives us the creeps? What causes something to be creepy? We are now in my bedroom, the bedroom I grew up in Kansas. Like a lot of children my age, I was terrified of scary stories to tell in the dark. But the very first book that ever scared me was The Curse of the Squirrel. To this day, I still haven't finished the book, but that's just me. Psychologist James Geer developed the Fear Survey Schedule 2, which he used to find out what scared us the most. Combined with the results of a more recent Gallup poll, these are the things that scare most of us the most. All of these things are scary, but are they creepy? Let's get more specific. I love the way Stephen King delineates 3 types of scary stuff. The first is the gross out. This is something disgusting, morbid, diseased. The second is horror. Horror to King is the unnatural, a giant spider, or being grabbed in the dark when you thought you were alone. The third, terror, is different, creepier. He says terror is coming home to find that everything that you own has been replaced with an exact copy. Terror is feeling something behind you, its breath on your neck, knowing that you will be grabbed, but then turning around to find that there was never anything there in the first place. Not a lot of research has been done on that feeling, the creeps, but many theories and ideas involve vagueness, ambiguity. For instance, masks and why clowns are creepy. Claude Lévi-Strauss wrote that the facial disguise temporarily eliminates from social intercourse the part of the body which reveals personal feelings and attitudes. Part of the reason even a neutral or happy mask can be creepy may have to do with ambiguity. A mask hides the true emotions and intentions of the person underneath. I don't know if the person wearing that mask is a threat or not. Vagueness is creepy when it comes to the human form. This is the famous uncanny valley. On a chart of humanness, there's a zone where something can be almost entirely human, but off by just a little. Not so wrong that it's clearly fake or funny, or so good that it's indistinguishable. Instead, it's just troubling. The creepiness of the uncanny valley is wonderfully demonstrated by John Bergeron's Singing Androids. Watch these videos when you're alone. A similar uneasy feeling comes from Shay St. John, a character created by Eric Fournier, funny to some, nightmare fuel to others. Uncanny humanoids, like all creepy things, straddle a line between two regions that we can understand and explain with language. Francis T. McAndrew and Sarah Kohnke describe being creeped out as an adaptive human response to the ambiguity of threats from others. Creepy things are kind of a threat, maybe, but they're also kind of not. So our brains don't know what to do. Some parts respond with fear, while other parts don't, and they don't know why. So instead of achieving a typical fear response, horror, we simply feel uneasy, terror, creeped out. Between the mountains of safety and danger, there is a valley of creepiness, where the limits of our knowledge and trust and security aren't very clear. Will looking at this cause you to die 1 week later? Impossible, right? Maybe. That's the terror of ambiguity. We don't do well with ambiguity. When it involves our own intentions, it can make us lie. And when it involves danger, but no recognizable threat, it can make us think and feel some pretty weird things. Have you ever peered over a ledge, a railing, way high up, like so high up it made you nervous and dizzy, and felt something pushing you? Maybe even an urge to jump. Have you ever stood on a ledge with a loved one and realized that you could push them? It would be that easy. You really could do it. And maybe you do want to do it, or maybe it's just cognitive dissonance. The fact that your brain is having to deal with ambiguity. A recent study by Jennifer Hames at Florida State University dubbed this the high place phenomenon. When approaching a ledge and a dangerous drop, your survival instinct kicks in and you pull yourself away. But your balance and motor systems don't get it. Nothing is pushing you, and you don't normally fall or leap randomly. So what's going on? The part of your brain that processes intention might resolve this by determining that something must be pushing you, or that you might actually want to jump or push your friend, even if none of that is true. Now, we're not done with ambiguity yet, because our language reflects the gray area of terror and creepiness. Take a look at the word terror itself. We have horrible and horrific, terrible and terrific. Why is that? Well, through history, we never really figured out what to call powerful experiences, because they're both. They are full of awe, awesome, and they are full of awe, awful. We need them to survive. We need fears and the creeps to understand our size, our weaknesses. But on the other hand, avoiding them is pretty great too. The creeps is a physical reminder that the world is vague and full of ambiguity, but that we are cunning, always trying to figure things out, but nonetheless fragile. Is that terrible or terrific? Well, it's both, which, as a creepy ghost would say, is kind of boo-tiful. And as always, thanks for watching. Hey, Vsause, Michael here. Attachment. Of two people's lips kissing. The average person will spend about 20,160 minutes of his or her life kissing. And the world record for the longest continuous kiss is 58 hours, 35 minutes, and 58 seconds. But why do we kiss? I mean, if you think about it, it seems kind of weird, right? I mean, sure, today, kissing represents peace, respect, passion, love. But when the first two people in human history kissed, were they just kind of being gross? Well, let's begin with what we do know. Kissing feels good, and it's good for you. A passionate kiss burns about 2 to 3 calories per minute and releases epinephrine and norepinephrine into the blood, making your heart pump faster. Kissing, more often, is correlated with a reduction of bad cholesterol and perceived stress. But these positive effects didn't become widespread by accident. Why did brains and bodies that love kissing become so common? Well, a popular story holds it that Pac-Man's shape was inspired by the shape of a pizza with a slice missing. But Toru Iwatani, the creator of Pac-Man, admitted that this was only half true. Pac-Man's shape was also inspired by rounding out the shape of the Japanese character for mouth. And it's mouths and Pac-Man's favorite activity, eating, which together bring us closer to the heart of the kiss. Evolutionary psychologists have argued that what we know today as kissing may have come from kiss feeding, the exchange of pre-chewed food from one mouth to another. Mother birds are famous for doing this, and many primates are frequently seen doing it as well. Not that long ago, it was common between human mothers and their children. In fact, before commercially produced or DIY baby food instructions were readily available, it made a lot of sense. Recently, Alicia Silverstone uploaded a clip of herself mouth-feeding her child. It seemed strange to some people, but even though, yeah, it exchanges saliva, which, like any contact with an infant, can transfer pathogens, healthy mothers and healthy children can benefit from the fact that kiss feeding provides nutrients, carbohydrates, proteins, iron, and zinc, which are not always available in breast milk. Plus, an adult's saliva can help pre-digest the food, making vitamins like B12 easier for the baby to absorb. So mouth-to-mouth attachment has a history of intimacy, trust, and closeness. Your saliva also carries information about who you are, your level of health, and mucous membranes in our mouths are permeable to hormones like testosterone, making a kiss a way to taste test a potential mate. A good kiss can be biological evidence that your kisser might be a good mate. So as a strategy for mate selection, prehistoric people who enjoyed kissing and did it more often may have made better decisions, picked better mates, reproduced more successfully, and eventually become the norm, giving us, people who love kissing. Any infant could have seen those benefits coming from a mile away, even though an infant's vision isn't that great. From birth to 4 months, babies can only focus on things about 8 to 10 inches away from their face, which not surprisingly is about the distance to their mother's face while breastfeeding. So faces, especially those looking right at us, tend to be the very first things in our lives we can focus on and see clearly. This might explain why we are so good at detecting faces. Humans are off the charts when it comes to this. In fact, we tend to see faces even when there aren't any. It's called pareidolia. Because humans are so cooperative, it makes sense for us to be good at recognizing faces, and more importantly, detecting when someone is looking directly at us and clearly expressing when we are looking at someone else. A predator who lives by not being seen needs a gaze that's less obvious. In fact, research has shown that our surprisingly white scleras, the area that borders the iris, isn't just an accident, but is a vital piece of human eye morphology that makes it easier for us to ascertain the direction of someone else's gaze at a glance. We also have impressive gaze direction networks inside our brains, containing individual neurons that fire when someone is staring directly at us, but that stop firing if the gaze shifts just a degree or two. So yeah, you can tell when you are being watched. We humans are quite sensitive to it, even those of us with scopophobia, the fear of being stared at. But to be sure, in order for this to work, the other person's gaze must be within your line of sight, your field of vision, that is, you can see them. Otherwise, if the stare is coming, say, from behind, there is no evidence that people can tell they are being watched. The psychic staring effect falls within the realm of pseudoscience. No widely accepted studies have ever found evidence that it exists. Anecdotally, what's more likely is that the very act of rubbernecking to see who's watching causes people to look up and for your gazes to attach. But what about attachment when no one is watching? One explanation for an infant's love, attachment to their mother, doesn't involve vision or staring, but instead food. The idea is that we love our mothers because as soon as we are born, they are a source of life-sustaining nourishment. But what if that nourishment came not from a loving mother, but from a scary wire mother? In the 1950s, Harry Harlow conducted a series of famous but controversial experiments on monkeys at the University of Wisconsin-Madison. Harlow's findings had substantial implications on our understanding of attachment, but by today's standards, his work would largely be considered unethical. In one of his most famous experiments, Harlow separated young monkeys from their mothers as soon as they were born and stuck them in cages with 2 fake mothers, a soft one wrapped in cloth that did nothing, and a cold mechanical mother made of wire that nonetheless did provide food. But despite being a cupboard mother, the young baby monkeys didn't bond with her. When Harlow or his team scared the baby monkeys with a strange contraption, the monkeys ran and clinged not to their wire source of life-sustaining nourishment, but to the soft, cuddly, and otherwise useless cloth mother. This suggested that warmth and comfort was more important than food when it came to nurturing attachment. Harlow also built a rejecting mother, which used a blast of pressurized air to push baby monkeys away. But instead of Finding another source of comfort, these monkeys clung even tighter at all times than monkeys raised without rejecting mothers. And this is what blows my mind. The instinct for warmth and comfort in newborn creatures is so strong, it not only resists attempts to frustrate it, but is paradoxically strengthened by it. Eckhard Hess tested this by using electric shocks to discourage ducklings from following the object they were imprinted on. But it only strengthened the behavior and made them follow more closely than ever before. The fact that a wire mother, or a rejecting mother, or receiving electric shocks for attaching to your mother would cause more attachment, more love, more dependence, seems like a paradox. But paradoxes can teach us. As Oscar Wilde put it, a paradox is the truth standing on its head to attract attention. And what gets our attention here is the effect uncertainty can have. In 1955, A.E. Fisher conducted an experiment on puppies. His team separated puppies into 3 groups. Members of the first group were treated kindly every time they approached a researcher. Members of the second group were punished for approaching the researchers. And puppies in the third group were randomly treated kindly or punished. They grew up never knowing what to expect. Their world was not a world of kindness or punishment, but rather one of uncertainty. What's really chilling is that the study found that that group, the third group of puppies, wound up being the most attached to the researchers. The third group loved the researchers the strongest and was the most dependent upon them. Guy Murchie called this the polarity principle. Stress, including the mental stress of uncertainty, is an ingredient in attachment or love, and perhaps even manifestations of hatred, its polar opposite, somehow enhance love. Uncertainty, psychologically, can lead to some of the greatest feelings of attachment and dependence. Good things and bad things in our lives often seem random and out of our control. So it's no surprise that we often react with blind love and acceptance in the face of an unfair existence, because what else are we supposed to do? We are that third group of puppies. But investigating uncertainty, conquering it so as to make the best decisions possible, is advantageous. So over time, life has favored activities that turn uncertainty into knowledge. Not every person out there is the best mate for you. But if it didn't matter which one you picked, a kiss, a taste test, wouldn't be necessary, and it wouldn't need to feel so good or bring us so much pleasure. So go out there and kiss someone today. And as always, thanks for watching. By the way, tomorrow I am headed to the European Space Agency's spaceport in South America with Euronews to watch a rocket launch in real life. Do you have any questions about space or space travel today? Let me know in the comments below and I will ask the experts your questions.